Cables present an interesting challenge in structural analysis because when you first install a cable, it connects 2 points with a straight line. But once load acts on it, its deformed shape changes the internal forces. So we have to consider the shape under load. We're going to do that with a cable with concentrated loads. We want to determine the maximum tension generated in the cable due to concentrated loads and the sag that results from those concentrated loads. And the key concepts we're going to use are applying equilibrium to cable segments and predicting sag of a cable. Here's our cable under load with its deformed shape. The sag at point C is 2 meters, but we don't know what the sag at point B is. We want to determine the maximum tension in the cable and that sag at point B. There are multiple ways to approach any problem, and to highlight that, I'm going to approach this problem in a slightly different way than the example in your book. And here's our approach. We're going to start by applying equilibrium. To point B. Then we'll apply equilibrium to point C. That will give us simultaneous equations that we can express in terms of YB, the sag to point B. And so we'll solve those simultaneous equations for that sag, and then with the unknown sag identified, we'll be able to go back and find the tension in each segment and thereby determine which one is maximum. Let's get started. Step 1. We're going to apply equilibrium to point B. So I'll draw that point. We have unknown tension in segment AB, unknown tension in segment BC, our downward applied force of 40 kilonewtons, and our geometry is such that the tension in segment AB has a rise of YB over a run of 1. And our tension in BC has a rise of YB minus 2. It's this distance right here over a run of 3. So let's start by summing forces in the x direction. We'll pick to the right as positive. The contribution from segment AB is negative, and if we take the horizontal piece, the length of the hypotenuse here will be the square root YB squared plus 1 squared, and that's the portion of the tension AB that acts in the x direction. We add the portion from BC, that's 3 over this hypotenuse which is yb minus 2 squared plus the 3 squared. Now we can rearrange this algebraically to express it in terms of the tension in AB over its hypotenuse. And that'll be helpful to us later. Now let's apply vertical equilibrium. We'll choose up as positive for our summation. We have the vertical piece of the tension in AB. We have the vertical piece of the from the tension in BC, and that's yb minus 2 over that hypotenuse. And we have the downward applied force. Well, if we take this and take a look, we'll see it right here multiplied by yb. So I want to substitute this for this part, and it'll give me 3yb yb minus 2 squared plus 3 squared times tension in segment AB plus yb minus 2 square root of yb minus 2 squared plus 3 squared. Ooh, that was BC, not AB. We substituted out AB. And BC minus the 40 kilonewtons equals 0. So now I have the same denominator for each of these two. Both of them are in terms of the tension in BC. So let's consolidate terms. We'll get 4 yb minus 2 over that hypotenuse equals 60 kilonewtons. And we'll call this equation 1, and we'll come back and use it in a little bit. Now step 2, we'll apply equilibrium. To point C. So I'll draw my point C. We have our downward applied force of 60 kilonewtons. We have our unknown segment force in BC. We have our unknown segment force in CD. Our geometry is such that we have a 2-meter rise over a half-meter run for segment CD. And we have the same slope that we looked at in the last free body for segment BC. So now let's apply horizontal equilibrium. We'll sum forces in the x direction, and we get a negative contribution from segment BC. get a positive contribution from segment CD. And if we shuffle terms to get just the tension in CD over its hypotenuse, we get the following. The 0.5 goes in the denominator, which means we get 6 in the numerator. Now let's apply vertical equilibrium. We'll choose up as positive for our summation. We get the downward component from segment BC. We get the upward component from segment CD, and we get the downward applied force of 60 kilonewtons. Now I want to take this expression and use it here, recognizing that this term is this one pre-multiplied by 2. We'll put the 2 on this, and so we'll find we still have the same first term, only now we'll have 2 times the 6, we'll have 12. And this time we'll get it right. It's the tension in segment BC minus the 60 kilonewtons equals 0. And so now I'm going to consolidate these terms, move that one to the other side, and I'll get 14 minus YB over that hypotenuse is equal to 60 kilonewtons. And we'll label this equation 2. Now we're ready for step 3. We're going to solve for the sag at point B. We're going to take those 2 equations we labeled. We're going to divide equation 2 by equation 1. And when I do that, we see that the tension in BC is in the left side of both equations. The hypotenuse length for segment BC is in the denominator of both sides. So what we get is the ratio of the numerators on the left, 14 minus the sag over 4 times the sag minus 2, and then it's the ratio of the applied loads, the 60 kilonewtons over the 40 kilonewtons, which is 3/2. So if I take this side and move it up, and I take this side and move it up, we're going to get 28 minus 2YB is 12YB minus 6. We'll consolidate YB on one side, we'll consolidate the other numbers on the other, we'll get 34 is 14 YB. The sag, 2.43 meters. Now we're ready to find the maximum tension. Among the three cable segments. To do that, we're going to substitute the value we found for the sag into equation 1, which we had generated from our equilibrium at point B. So we have 4 times the sag minus 2 over the square root 2.43 minus 2 squared plus 3 squared. That gave us the component of the tension in member BC that was equal to 40 kilonewtons. We solve that for the tension in BC, we get 15.7 kilonewtons. Now let's use this value to find the tension in AB. And to do that, we're going to use this relationship that we generated. I now have the tension in segment BC. Let's solve this relationship to find the tension in AB. So we have tension in AB divided by the square root 2.43 squared plus 1 squared is equal to 3 times the tension in segment BC, which we just calculated, the square root 2.43 minus 2 squared plus 3 squared. Solve that for the tension in AB. We get 40.9 kilonewtons. So segment BC does not have the peak tension. But now let's look for segment CD. And to do that, we're going to use this relationship that we derived earlier. Again, we have the tension in segment BC. We'll solve this relationship for the tension in CD. So we have the tension in CD divided by 0.5 squared plus 2 squared equals 6 times the tension in segment BC divided by the square root 2.43 minus 2 squared plus 3 squared. Solve all of that for the tension in CD to find 64.1 kilonewtons. And of the three segments, segment CD has the maximum tension. Great. Now let's go back and review the process we followed. We started by applying equilibrium to point B, where we had 2 cable segments and the 40 kilonewton applied load. Now there's 3 unknowns and only 2 equations of equilibrium, so the best we could do was consolidate them equations to get it down to 2 unknowns. And we chose to use the sag at B and the tension in segment BC. And we chose the tension segment at BC because it'll be common to the equilibrium we'll look at point B or point C. So we then repeated the process at point C. Again, 3 unknowns, 2 equations of equilibrium, but 2 of those unknowns are the sag at B and the tension in segment BC. So we consolidated those 2 equations to get 1 equation in terms of the 2 unknowns, sag at B and the tension in segment BC. So we had labeled those equations 1 and 2, and we divided equation 2 by equation 1, solved it for the sag in B. We then substituted that sag value into equation 1 to get the tension in segment BC. We then used a previous relationship to get the tension in AB and the tension in CD given the tension in BC values, evaluated or looked at the three of them, found the maximum tension, and it's in segment CD. Well done.